Welcome back to Module 205I Part 2. Now we're going to be looking directly at different types of electrical drawings as well as the symbology and how to use those drawings. The first type of diagram we're going to look at is a one-line diagram. One-line diagrams are used in order to depict what the interconnection between different components are. They have no real value as far as where are we placing the components. They do give us a graphic representation of what is involved in the system and how it is all interconnected. One-line diagrams, also called single-line diagrams, use simple geometric shapes. They show the basic interconnection. They're not put to scale and they're not physically accurate, but they are a general orientation of components. Some one-line diagrams will also give you notations about overload, wire size, and conduit size. A riser diagram is a different type of one-line diagram, and it gives me the advantage of seeing the perspective of height on my job site. Not only can I see the interconnection of all my different parts, but I can also identify which floor to find certain parts on. With the drawing on the screen, I can see my service entrance and distribution panel feeding three different other panels. Two of them on the first floor being panel board P1 and panel board L1. On the second floor is where I would find panel board P2. I can't see how far apart these panels are, but at least I can see what I need to do in order to interconnect them. Block diagrams are the simplest type of one-line diagram that we have. Their purpose is just to show us components and the interconnection of the components. It doesn't tell us anything about the wiring, it doesn't tell us anything about the sizing, but this will tell me what I'm expecting to find within the system and approximately where in the system that they should be located. After one-line diagrams, schematic diagrams are a much more complex set of diagrams that we have, and there's a specific purpose to using schematic diagrams. Schematic diagrams are also called ladder diagrams since the circuits appear as the rungs of the ladder. They're built using vertical lines to indicate our power source and the horizontal lines to indicate our circuitry. They're best used for troubleshooting since they show the sequence of operations. Any of our devices within our schematic needs to be shown with no energy. This means I don't have any power on, I have not pushed any buttons. If I had a thermal switch, I don't have any heat. If I had a pressure switch, I don't have any pressure. We want to show all the buttons and all the devices in their normal status without anything affecting them. When I'm arranging my devices inside my schematic, I always want to follow the same pattern. I want to have my control devices on the left and my load devices on the right. This makes it easier for me to design my schematics and it makes it easier for other people to read them. Anytime I have any interconnections between the different circuits inside my schematic, I should always show it with a node or a dot. It's also important to try to avoid any crossed lines. Crossed lines could be misconstrued as a connection point, and we don't want that, otherwise we would be building our circuits incorrectly. We should also be looking for related objects inside the schematic as well. Anytime that we have a coil and contacts, if those coils and contacts are related to each other, they should show the same symbols. In the drawing that we have on the screen, we have two coils, one labeled F and one labeled R. Within the drawings, we can also see different contacts. We have two contacts labeled F and two contacts labeled R. This tells me when I energize my F coil, both those two F contacts are going to change state. The normally open one will close and the normally closed one will open. And same thing for the R coil. When we have very large schematic diagrams, they can get very complex and confusing. Therefore, we use rung numbering in order to make them a little bit easier. On the left-hand side of the schematic, you see a bunch of numbers. Each one of those numbers represents a different rung within the drawing. On the right-hand side of the drawing, you'll also see numbers. What those numbers represent is that if there is a coil in the line of that schematic, the numbers on the right-hand side tell you where the contacts for that coil can be found. For example, on line 1, we have coil M1. So on the right-hand side, we see the numbers 2 and 3. That means M1 has a contact in line 2 and another contact in line 3. This way we can go through the drawing, identify the contacts that are related to any one coil, and we know what's going to operate next. This helps us with our troubleshooting and our order of operations. When it comes to schematic diagrams, they have their own terminologies that we would not find in other types of drawings, such as control circuits, pilot control devices and interlocking. Within a schematic diagram, we typically have two different types of circuits. The first circuit is a power circuit, and the second circuit is the control circuit. Within the power circuit, we would find the electrical load that we want to power up. It would also contain any control devices needed to operate that load, such as the contacts that are operated by a coil inside the control circuit. The power circuit is operated by the control circuit. The control circuit itself is considered a remote circuit because it is mechanically connected to the power circuit, but is electrically isolated. Within the control circuit, I would have a coil which would operate the contacts within the power circuit. However, in my control circuit, I would find other devices for the operation of the power circuit, such as the stop and start buttons and the holding contacts. Both types of circuits can have pilot control devices. The definition of a pilot control device is any device that can be used to control something else, such as buttons, switches, contacts, and coils, since coils control the contacts. Things that would not be included are the pilot lights. Within some schematic diagrams, I can also identify three different types of interlocking. The first type of interlocking that we have is called mechanical interlocking. With mechanical interlocking, if I have two different coils that I cannot have operating at the exact same time, such as in a forward and reversing starter, I want to be able to mechanically block one armature from moving, and that's what mechanical interlocking does. On a schematic diagram, I represent that as a hatched line indicating that armature that is connecting those two coils. The second type of interlocking I can find on my schematic diagram is called electrical interlocking. Normally, we would use normally closed contacts in order to achieve this. On the drawing that we have here, my F coil operates a normally closed F contact in the opposite string. So when I energize my F coil, it opens up the F contact in the reverse circuit. That means the R coil can never energize until the F coil is de-energized. And this is how my electrical interlocking works. The third type of interlocking I can find on my schematic diagram is push-button interlocking. Inside the labs, we've been able to use buttons that are both stop and start. They're normally open and normally closed. These type of buttons physically have two different contacts on the inside. One is normally open contact, one is normally closed contact, and by activating the button, I change the state of both those contacts at the exact same time. Inside my schematic diagram, I represent that connection with a hatched line. If you look at the start button on my forward circuit, you'll see the hatched line going to a stop button on my reverse circuit. These two are interlocked, so when I press one of those buttons, they both change state at the exact same time. Now that I can recognize different circuitry, different devices within my circuits, as well as the interlocking that I can find within my circuits, I can use that information to start to figure out the sequence of operation in my schematics. I'm always going to follow my lines from left to right, and I have to keep in mind what the labels are telling me. Be aware of any holding contacts and auxiliary contacts you might find as well. We're going to be looking at the sequence of operation of the circuit here. When we first energize the circuit, what we find is that L1 is connected through all the normally closed components, and they stop at all the normally open components. L2 would go through all the normally closed components and stop at all the load devices. So on L1, line 1 goes through the normally closed stop button, but stops at the start and the M1 open contact. Then lines 3, 4, 5, and 6 all stop at open devices. L2 goes through the overload contacts on lines 1, 3, and 4 to stop at M1, M2, and M3. So we can see here we are providing power to all the open devices, and we have a return path to all the loads. We need to be aware of the holding contacts, which is here. We also need to be aware of all the auxiliary contacts, which are over here. And of course, these are going to operate as our coils are turning on as well. Let's see what happens when we hit the start button. As I press down on the start button, I have power that goes through the start button to coil M1. When coil M1 is energized, it closes both contact M1 on line 2 and on line 3. This provides a constant power to coil M1 even when I let go of the start button. This, of course, is my holding contact. On line 3, I'm also providing power directly over to coil M2. which energizes that one. As N2 energizes, it closes the contact on line 4, which then provides power over to coil M3. And then coil M3 is energized. You'll notice nothing has happened to lines 5 and 6 yet. In order for anything to happen to lines 5 and 6, I would have to close the pressure switch on line 5. When the pressure switch on line 5 is closed, then it now provides power over to coil C. As coil C is energized, it closes the contact on line 6, which then in turn energizes the light. Between lines 5 and 6, this is a separate circuit from everything else inside the system. There's nothing on lines 1, 2, 3, or 4 that affect lines 5 and 6. Therefore, line 5 and 6 would simply be an alert circuit. So when the pressure got high enough, it would turn on an indicator light telling me that I have a high pressure situation. By understanding how schematic diagrams work and understanding the sequence of operation within a diagram, we can use that information to troubleshoot it. We're going to analyze the diagram that we see on the screen now, and then I'm going to give you certain scenarios of what could possibly be wrong with the circuit. I want you to pause the video after I give you the scenario, and you can figure out what is wrong, and then you continue to see if you're correct. First, let's take a look at what this circuit holds. We're going to identify all the different holding contacts that we have inside the circuit. This circuit has 4 different holding contacts, and they're all in parallel with certain start buttons. If I were to have something that was not holding but would start, I might think maybe there's a problem with the holding contact. I should also be able to identify any interlocking. The interlocking contacts are here. Contact 3 and 4, which are normally closed contacts, we can recognize from the previous drawing that we saw. But contact A1 is also an interlocking contact, since coils 3, 4, and 5 would not start unless coil A1 was energized. That makes that an electrical interlock as well. Now that we are familiar with some of the things on our drawing, let's take a look at diagnosing the troubleshooting. Here's your first scenario. Coil M5 will start, but as soon as I let go of the button, it stops again and will not continue to run. Pause the video, analyze the circuit, and try to figure out what exactly is wrong with the circuit. Normally open contact M5 here would be the problem. This is my holding contact for my coil, so therefore if I can start my coil, but when I release the button my coil does not stay energized, it means I have no holding path, therefore it's my holding contact that is the problem. Here's your next scenario. When I press the start button ST1, both M1 and A1 will start normally. However, M2 will not start. What is going to be the problem? Pause the video and see if you can figure it out. It would be my auxiliary contact A1 that would be the problem. Since M1 and A1 started, I know that S1, ST1, and holding contact M1 all work, as well as overload contacts 1 and 2 are both still closed. This means I still have continuity through those two circuits. A1 is what's providing power over to M2, so therefore that's the only thing that could be wrong that's affecting only that one coil and not the others. Of course, I don't know anything about M3, 4, and 5, so I don't know what's happening with those, but they weren't really part of the problem. Alright, so now the next scenario is a little bit more complicated, so pay attention. If I have coil M4 operating, I cannot start coil M3. However, if I have coil M3 operating, I can start coil M4. What would be the problem? If you remember when we first looked at this circuit, we identified the normally closed contacts M3 and M4 as being interlock contacts. Since they're both normally closed contacts, this tells me that both M3 and M4 should not run at the same time. They should be locking each other out. So therefore, if I can operate M3, and then I can still start M4, that tells me my interlocking for M4 doesn't work, which also tells me that the normally closed contact M3 is going to be faulty. Here's your last scenario. When I press button ST1, M1, A1, and M2 all operate normally, but no matter what I do, I cannot get M3, M4, or M5 to start. What is going to be the problem? The only thing that is associated with M3, M4, and M5 that has nothing to do with M1, A1, or M2 is the overload contact number 5. This must be open. You might think it might be contact A1, but contact A1 is still controlling M2. And since M2 is working, we know that A1 is also working properly. I hope you got all those different examples. I hope you understand how we can use a schematic like this to troubleshoot circuits as long as we understand what the order of operations are going to be and what each device inside the circuit is supposed to be doing. We can figure out what's wrong with the circuit as we go through it. You've now reached the end of 205I. Please return to Blackboard and do the knowledge check. After you've done that, go ahead and do the review test for this module and continue on to 205J.